Good morning, everyone. Welcome to this morning's webinar. My name is Gavin Fields, and I'm a Senior Water Resources Engineer on the other side of the hemisphere in Brisbane, Australia. And with me this morning is Dr. Bill Syme from BMT WBM. And we're here to present this morning's webinar on direct rainfall. This is the sort of the last of our 2D modelling series. But I will note that this afternoon for American time, it's early morning for us, but today's webinar is independent of the previous two webinars, so don't feel under pressure that you had to have sat in on the previous two that we've run with Bill. Of course, this webinar is part of our XP Live educational program, and there are obviously several pre-recorded webinars that are available via our website. And today's session, in terms of talk time, we'll go for probably about 45 to sort of 50 minutes, leave about 10 or so minutes for questions at the end, and we're very keen to hear from you over the course of the webinar. We obviously have other engineers sitting in the background ready to answer questions as we go through this morning's session. So yes, that's me, Gavin Fields. And so again, that's Bill, again, for those who aren't sitting in live. So this morning's session, of course, is on direct rainfall. Oh, beg your pardon. And what we'll do, I'm going to pass over to Bill shortly. He's going to run through an introduction and an overview of the theory and application of direct rainfall in 2D modelling. Towards the back end, I'll give a bit of a demonstration on a couple of case studies that highlight the efficiency that can be gained by using this particular method. And of course some Q&A at the back end. So thank you again for joining us. Hopefully we've certainly been watching the numbers grow as we've just run this introduction. So we're right to kick off, and I'll pass over to Bill.
Thank you, Gavin, and welcome everyone from a cold, sunny morning in Brisbane. Very early here. So direct rainfall. So what's happening here is instead of applying some flow boundaries to your model, you're actually applying rainfall directly to your 2D cells. So there's actually no hydrological modelling, there's no unit hydrographs been put into the model. You're just basically putting rainfall directly onto your 2D cells, and you are relying on the 2D solution to route that water through your model in an accurate way. One of the reasons it's very attractive and it's starting to be used a lot is it's actually very easy to set up, which that's a big plus, of course, but there can be minuses, which I'll talk about. A very important issue that I'll keep iterating during the presentation is that this is a new approach to the industry to some extent, certainly in the hydraulic modelling area. So it is very important that you, like all modelling, you review your results. You must always question what is coming out of any model. So when you apply this rainfall to the grid, the rate of runoff and how it moves around is dependent on a number of factors. Obviously, the mesh or cell area would have some bearing on things. So if you have a very fine mesh that's able to pick up much more details in the channels, you may get a different sort of outcome than if you're using a very coarse mesh. And that's one of those things that's always just good to sensitivity test and get a feel for. Clearly, the amount of rainfall that falls on has a bearing on things. But one of the big ones is actually the roughness value you apply, because a lot of your model is likely to be flowing literally only a millimetre or two deep. So, the big question is the managed roughness equation, which tends to dominate at those shallow depths, the appropriate for those very, very shallow flows. Clearly, the slope between cells has a bearing. Once again, much of your model in the outside your flood-prone areas will be running very shallow. The slope will have a big bearing on things, as you would expect. And one of the really big ones is the rainfall losses and infiltration into your ground. In some parts of the world, this is a very, very major part of the water balance during a storm event. So as it comes off, the flow effectively moves in 4 directions, and the storage is sort of controlled by your 2D grid. A really nice thing about this approach is that it's fairly seamless. As your water comes off the steeper parts and into your flood-prone areas, you're straight into the hydraulic. You're using the same equations. We're using the full 2D equations. We're not using 1D equations. We're using the full 2D equations. So once the water hits the deeper parts of your model, starts to move down your rivers and creeks and so forth, you will be modeling all the terms of inertia and eddy viscosity. So it's a very seamless transition. There's the same equations being applied whether you're up in the hills or down on the floodplain. Now, where would you apply this method? Well, it's very, very attractive where you have very flat terrain, because often it's very hard to delineate where your sub-boundaries are for your catchment or hydrological modelling. And so it really makes that process easy to decide on how to, well, you don't have to decide anything, you just let the modelling decide for you. And Gavin will be showing a nice example at the end that demonstrates that. Sometimes you also have, in flat areas, you have catchments can start to interact, and once again that can be very hard to determine whereabouts that would be happening. So once again it will automatically pick up any overflow into neighbouring catchments or floodplains, and that tends to happen quite a bit in the lower parts. Detailed urban studies. It's been used, certainly being used a lot out here for your urban areas, because it's just very easy to apply, and you're picking up the resolution of your land use at a much finer resolution than a catchment model. You can get down to delineating buildings and roofs and gardens and roads, and with an underlying pipe system, it's a very, very powerful combination. And so in many respects it simplifies the modelling process, not from a computational point of view. Computationally we've gone up a few notches, but in terms of setting up your models, making it easier to produce these models, this is a great approach. A number of advantages and disadvantages with any sort of modelling. You need to understand those. As we've talked about, the big pluses are you don't need a hydrologic model, or you don't need to apply unit hydrographs. You don't need to make assumptions where your outlet locations are. That will just come out. If you've got cross flows between catchments, you do not have to work out where that will be or have separate models. And any sort of effects from overland flow are just directly incorporated. So rather than putting all your flow down the bottom of your model, you'll see the flow happening all over your model. But it is a new technique, as I've mentioned. There's only been limited calibration of this technique to gauge data, so having calibration data is very, very important if you have it, and to use that data to verify what you're doing. And that's the case with all hydraulic modelling or hydrologic modelling. One of the big downsides compared to hydrologic modelling is there's a big increase in runtime. So, huge increase. So you have to be prepared for that. Hydrologic models tend to run very, very quickly, in a matter of seconds or minutes, and whereas these direct rainfall models can take quite a bit longer, of course. And even if you're just moving from a normal 2D model to a direct rainfall 2D model, you'll often see an increase, because basically every cell in your model is pretty well wet, and the number of wet cells will control the runtime or influence the runtime. You do need to have good digital terrain information, which tends to apply for all 2D modelling, and that's much more readily available today, but not always. But the quality of your model will be a function of your digital terrain information. If your grid is too coarse to define your smaller flow paths, and you haven't got those set up as 1D, or you can't get down to a finer cell size due to run times, you just need to be conscious of that. What's important is that your main flow paths or your objectives of your study are being met. So if it's a very quick, broad-scale model, it's not necessarily that essential to be down to a very fine cell size. But if you're doing a high-resolution assessment of an urban area that has issues, and you need to get down to your buildings and your fences and your pits and your pipes, well then of course you want to be down to a fine cell size. And as I mentioned before, we're still learning about the very, very shallow flows and how they're best modelled, and I'll talk about that a little bit further more. So your model setup, so that involves specifying, usual business of setting up your Manning's End roughnesses. The losses and the approach you take to losses are very important, or can be very important, and your cell size, as we've discussed. So with your model roughness, you can of course just set a constant roughness, and many modelers will just do that to get things going, get your model running. It's very quick. You just apply your typical Manning's End value. If you are calibrating or you're benchmarking or you're on the sensitivity test, you do need to get a feel as to what would happen. For example, grass, for example, if it's only a few millimeters deep through grass, then there's a strong argument that the roughness should be much, much higher. So you can certainly look at varying that roughness with depth. You would tend to just vary it from a very high rough value for very shallow depths up to, if the grass is only 50 mils high, if it's mown grass, you would transition to your normal Manning's End very, very quickly. If it's very long grass, you may go to a higher value before you transition to your normal Manning's End. But you can do that, and you can specify curves to do that. There's an interesting effect with buildings, which I'll talk about later, and some of the approaches taken with those. Now, your losses can be very, very important. If you're in a sort of tropical area with high rainfall and very low infiltration losses, it's a lot less important. But if you're in some areas of the world where infiltration can literally be 50, 60, 70, 80% of your water balance during a storm event, it is very important to be able to model this side of the equation. Now, there's two ways of applying losses. There's a very simple initial continuing loss, which you can apply to the rainfall. So this approach takes an initial amount off the rainfall, then a continuing loss off the rainfall. So it reduces the amount of rainfall that actually falls onto your model. It's not infiltrating into the ground, it's reducing the amount of rainfall that actually falls onto your model. Normally you would, if you're using an infiltration model, as I'll talk about in a minute, you would normally not use an initial continuing loss on your rainfall, except in some cases people may put a small initial loss. It's like an interception loss, which relates to the water being captured by vegetation or other things, or a bit of ponding that you think needs to be taken into account. So you're sort of saying that this water basically never infiltrates. If you're not using an infiltration model, as I'll talk about in a sec, you probably do need to apply this initial continuing loss values. Infiltration is, as I said, very important. You basically feed in layers of soil types, and each soil type can be associated with a different infiltration method. For example, you can have one soil using green amp, another soil using the Horton approach. The important thing is that you get a feel and test this. The three methods that you have available, two of them are available in the current version of XP2D. So you have the green amp method, which is the most sophisticated around for this type of modeling. You're not doing groundwater modeling here, but the green amp is probably the most sophisticated for getting your water into your ground. You feed in information about its hydraulic conductivity and so forth. The other method is just this initial continuing loss method. Now, the initial continuing loss method as an infiltration method is different to the previous slide in the sense that this is based on water that's ponded. So we're not talking about affecting the rainfall here. We're talking about water that's sitting on your model and infiltrating into the ground. So you can actually apply a similar initial loss continuing loss that will extract water into the ground. Now, all these methods just apply on all your wet cells. So if the rainfall stopped, they'll continue to lose water into the ground, which is quite nice, certainly post rainfall, post flood. The Horton method is going to be available in the 2015 SP1 release. So that will also be another option. The Horton method just reduces continuing loss, similar to continuing loss approach, but it reduces the loss rate over time, and in some parts of the world it's quite popular. So direct rainfall in urban areas where you have buildings, and one of the interesting topics of discussion is how do you handle buildings, and there's a variety of views on this. One of the ones that I quite like is that when the water, if the building is located on the sort of steeper parts or the areas that don't really experience flooding, basically the water will be just falling on the roof the whole time and draining quickly onto the ground or possibly into your pipe system. So the mannings end in those very, very shallow depth areas should be very, very high. So, sorry, very, very low. So basically you're representing the roof. So you want the water to slip off very, very quickly. If you do want water to move into your pipe system, some modelers actually divide the amount of rainfall going on as direct rainfall, and they also have rainfall going direct as a hydrograph directly into the pipe system. So you can split it up if you wanted to. So once the water starts to get deep, if you have a building which actually floods, it has water depths greater than say a foot or so, the building essentially becomes a barrier to floodwaters or an obstruction to floodwaters. So what modelers tend to do is for those higher depths, if water does get that high, you're basically saying the building is in a flooded area and it becomes an obstruction. So you increase the Manning's N value quite substantially once you're, say, get above 0.1, 0.2 of a metre or around about a foot of water. So it's an interesting approach that's worked quite well in quite a lot of studies in Sydney and elsewhere, and certainly a nice way of modelling that sort of situation. So calibration and verification of these direct rainfall models, as we've said earlier, this is a new approach to the industry, and it's very important to recognise that with any modelling you need to understand what's going on, to proof your model, make sure it's doing what you think it should be doing, make sure it's doing what the evidence is out there. So if you can calibrate these models to historical events, that's always a big plus. And certainly there's some work going on in that area at the moment. Often it's very hard to come by calibration data, if it exists at all, and you don't have that luxury. Although I will add, if you are modelling an area that has experienced a storm, there's normally even just good information on where it did flood and so forth. So, there's always something around these days. Now, if you can't calibrate to historical events, you can always do comparisons with more traditional methods. It's not to say the traditional method is right, but those methods have been around often for many, many years and have, to a large extent, been proven by the test of time. And if you're getting vastly different results to a traditional method, you should probably question why that is and look at what may be causing that. By and large, we're finding that we're getting good matches, and in some cases we are looking at varying that roughness with depth to get a better match. In any modelling, it's very important to understand what your most sensitive parameters are. So sensitivity test your parameters. If your infiltration into your ground is a dominant factor in getting your modelling right, then that's what you should be focusing on. Your Manning's N values could be relatively fairly trivial. But if you're in a low infiltration area, your Manning's N and how you treat it at shallow depths could be very, very important. So it's very worthwhile to get a good feel for what parameters really have a big effect on your model results. And when you're calibrating or comparing traditional methods, you should focus on those parameters. As I said, it is a new approach to the industry. There is limited published data on this, but basically there is an increasing amount of work. There's a lot of people using this approach, and people are over time getting more and more information and coming up with parameters that they feel very comfortable with. So I think we'll continue to see more papers on this topic and so forth. And of course, you should always do your sort of standard volume checks, the amount of rain onto your model, is equal to the amount of water that comes off less any residual volume. So it's important to do that, of course. Not showing, this is in fact the only equation we're showing, and that's just basically following on from that last comment, your volume in equals your volume out less any residual. So, to help with that process, in XV2 you can look at say the cumulative mass error, which is more a measure of your model convergence. XV2D engine is a implicit solution, which means it uses matrices, and therefore it does rely on convergence to provide a good solution. It's fast and uses big time steps, but you do rely on that convergence to be a measure of how healthy your model is. Most direct rainfall models will require to be run in double precision simply because the amount of water falling on your cell each time step is very, very small, and you just need that extra precision for the solution. But anyway, if you're having problems with getting, if you've got a mass error more than 1% on your model, contact the support guys and they'll help you out with that. So traditional versus direct rainfall approaches. So on the left of the screen there, you have the output from a model which Gavin will demonstrate shortly. It's been modeled using a traditional approach. So it's got some sub-catchments there that are feeding water into parts of the model, and it produces probably quite a nice result in certain parts of the model. But what happens when you move to a direct rainfall approach is the middle screen, and basically every cell is wet, and most of those dark blue colouring there is actually very, very shallow flow, literally millimeters deep. So it's not really flooding. It's how it is in reality. It's basically just rain falling on the ground and running down into your lower points. So that's actually what's happening on your model. Well, how a lot of people present direct rainfall results, though, is to trim or cut off that that smaller, very shallow flow. And typically, the numbers that are used here are 5 to 10 centimeters. You tend to trim that water off. So basically, you're saying anything less than, say, 5 centimeters is not flooding. It's just water that's moving, either just sheet flow or moving around. And so the third image on the right is the same as the middle one, but with not showing anything below 75 millimeters. And as you can see from the left and right images, you get some quite similar patterns in the ponded areas, not in the very shallow ground, but in this area here, on that where the sort of reaches near those houses. The results are quite similar, which is a good sign. But once you get into this very flat terrain, you get quite different results, because basically this is very, very flat, that northern part of the model, and with the traditional approach, you just doesn't know where the water really goes. With the direct rainfall, it just puts it on all the cells there, and you can see on the left-hand side there's quite a large ponded area. So it gives you a much better feel. You don't have to worry about delineating catchments and so forth, and hopefully good results. So on the results side, this is a good example. So on the left here is the flow out of this model, and this is the more traditional approach. So it peaks around 3.5 cubic meters per second, a little bit after 1 hour. On the right is the direct rainfall approach, and it peaks higher. It's a shorter, sharper runoff hydrograph at 5.5 cubic meters per second, about half an hour earlier. So you are getting reasonably different results in this case. And it's not to say either one is right. And once again, you have to sensitivity test. So, if the left-hand one was some sort of recorded or calibration data, you would definitely be heading in that direction, and you would be doing things like roughening up your Manning's values at very shallow depths to delay that hydrograph coming through. And so that's why it is important to question your results in any modelling, and if at all possible, to calibrate and verify to historical events. For those who want to do some more reading on this is an Australian publication, but it was put together several years ago, and there's a very good chapter inside it on direct rainfall. And back then, this approach was starting to be used quite a lot, and rightly so. There's quite a bit of concern in the industry that people were not really understanding the limitations and whatever. It's a great approach and you get some great results, but you do need to be aware of you just don't throw your rainfall in your model and assume it's right. So and that applies with hydrologic modeling. You can get vastly different answers depending on what parameters and how you set up your model. So it is important to understand what's going on. If you'd like to do some more reading on this document is available via the web. There's a link there on the bottom right of the screen. Download it, have a read, and it's hope to give you some good, more insight to what's going on. So I'll now hand over to Gavin, who's going to give a live demonstration of that model, and I'll chip in at the end with some answers to questions. Thank you.
Thanks, Bill. That was great. So for those of you who may or may not be a current user of the software, obviously we have two core packages that have the XP2D module. So XP2D itself is not actually its own independent program. It's a module that sits within both XP Swim and XP Storm. So in today's demonstration, I'm using XP Swim, but fundamentally still the same in both applications. Oops, I've gone back. I've got to jump out of this and go over to my model. So I've got two case studies that I'm sort of going to quickly run through. So I'll just turn those results off. And I have a relatively simple site, I'll call it. I have an urban area that discharges into a very flat area of terrain to the north. It's quite close to the ocean. And the northern extent of this particular model is actually bounded by a tidal condition. So the software in boundaries, with head boundaries and flow boundaries on the 2D is very flexible in either static or variable dynamic boundary conditions. So it's very useful to modelers. I just like to sort of run through the process that I would typically go through in preparing a model. I typically say to most users on this side of the hemisphere that as you're going through a model, one of the starting points, you always want to have a good aerial photo. Those aerial photos just put us into frame straight away, particularly if it can be geo-referenced. And then the next core thing, of course, is our subsurface infrastructure. Those pure 1D elements, the pipes, your inlets, your outlets, head walls, etc. And these days, often they can either be picked up from GIS databases, whether or not your local authority may or may not have that available or publicly available, or alternatively, you may need to engage the services of a surveyor to pick up those points. But in terms of data collection, in conjunction with some surface information, be that in LiDAR or ALS or aerial survey formats, very quick to put a model like this together. Those electronic databases just make life a dream for modelers of stormwater. So very quickly we can build a model like this, and I'll just turn that surface back on. But that LiDAR surface had a 1 meter point resolution, and then we're throwing our 2D model over the top of this. Now, to get to this point, effectively, we could be at this point within 10 to 15 minutes, almost no time at all, if we were just trying to prepare this model on that front. So very, very efficient. But of course, data is king. Now, this particular model was actually set up originally as a traditional catchment-based hydrologic model. And so if I turn on the sub-catchments here, we can see that we've got lots of little sub-catchments that had to be drafted up, determined and then applied to the inlet points, all the points of interest in this particular model. Now, at times that can be tedious. This is only a small example. We can see quickly how many sub-catchments that have been defined on this particular model. Conversely, if we were to move to a direct rainfall method, we wouldn't go through this process at all. We would simply identify typically the major catchment boundary if you're going to do a complete catchment direct rainfall model. And some people will say, well, do we need to extend our model beyond those upper catchment boundaries? And look, sometimes that can be useful to just to ensure there's take care of any major inter-catchment or cross-catchment flows. But generally speaking, covering the whole catchment is generally good enough. And just to give an example, if I zoom in on this particular model, if I can grab my icon there, and I'm just going to zoom in around this northern section of the urban area. And in this particular model, if I pick this park, that park, if I go and interrogate, so I beg your pardon, I'm in the hydraulic mode. If I go to the runoff, our runoff layer, you could use any of the different methods inside our software, but we can see that this particular catchment, I apologise, our unit discussion as well this morning, Bill and I are in the metric world. We apologise for that. We should possibly be talking in feet and inches. We've probably mixed that up. But this particular catchment is just shy of half a hectare. So that's a couple of acres in US terms. And you could apply the EPA runoff method or other method as required for your local area to generate a hydrograph. And that hydrograph would not show any surface flows in the upper component of that catchment. The flow starts at that point. And that's the core difference that I see between traditional methods to the direct rainfall method. So if I just zoom out a bit, again, I'll turn these catchments off and zoom out to this model, and I'm going to turn on our water depth results just to have a look at how this traditional method operates. So I can hit play down the bottom left-hand corner, and as this storm propagates, it's a brief storm, it's about a 60-minute storm on this catchment that we've applied today, and about 8 or so minutes, the minor drainage system is starting to reach capacity, and we're starting to take advantage of the terrain. And we can see the water discharging into the flat area to the north. But obviously the water is relatively well confined to the roadway areas inside the model itself. And thankfully, most of these properties are not prone to inundation back from the roadways. So look, that's a delightful view, and look, something that I believe has been, well appreciated by the industry really for the last decade or more. But look, it does relatively well. I'll stop it at that point there, and I'll transition to my second model. It's the exact same model, and the only difference between this one is that effectively we've disabled those 1D hydrologic nodes, and we've applied a rainfall boundary on this our layer under our 2D model layer inside the software. And effectively this sort of orange polygon is effectively my cloud, and we're saying to the model, this is where I'm interested in rainfall. Tell me the impact on this catchment from this point, very simple to apply rainfall to that area. And again, if I step through the maximum or the water depth results, and I hit play here, instantly we're seeing the whole model really subject to those very fine, sub-inch depths of water. That generally, in most of this model, we're not interested in. It's sheet flow, it's flows that are accumulating in backyards, in the park. But we can start to see as it is actually accumulating in the low points and depressions inside the system near the sag locations. That's where we're starting to get this sense of depth. And of course, inundation, and therefore risk to property, to cars, etc. Last week here in Brisbane, we did have a flash flood in the space of a couple of hours, and even in the street that I personally live in, luckily I'm on the high end, but there are about 15 cars written off with water over their roofs. Clearly, we need to understand those sort of catchments to try and give the public greater warning to protect not only their property but themselves. At the end of the day, most engineers aren't interested in that lovely animation that I just showed. They want to see maximum depth. We want to report these maximum inundation extents. And if I flick over I have this lab set always in our software now. It's the maximum water depth. You can also get maximum water elevation and all of the other standard 2D results. But what we've done very simply in the model, if I right click and go to its properties, I can filter out a given range. And so on the filter that I've applied at the moment, I'm cutting off the first 50 mil, or just shy of 2 inches, from this particular model. Again, I am in a metric version or instance of the software, so I apologise for that to all the attendees. Possibly a bit of unit conversion. And likewise, that's going up to 3.5 feet virtually in 1.1 meters. But if I were to take off, increase that to 0.75 of a meter, not 750 mil. I said that yesterday too. And again, we just sort of trim out some of those sort of localized ponding points, and really does clean up and get us closer to that traditional view of the software, of the output. Now, one thing that I'll note, that if I zoom into the urban area, we get these isolated ponds or depression points within the model. You might say, well, are they points of flooding? Look, my personal experience tells me, of course, that those points aren't connected to the general inundation points. They're local points. Some modelers will actually try and scrub those out from their reporting, and different routines can be applied in third-party packages at the moment, and there are some routines that we're looking at to isolate those ponds out within our interface as well. But generally speaking, those isolated pond points are just irregularities in the terrain or the input data itself, and not key contributors to floodplain extent. So look, that's a very traditional comparison, I suppose. And in the graphs that Bill showed before, with that 3.5 cubic meters to 5.5 cubic meters of flow coming from this respective catchment, look, we would want to go back and have a look at the depths of key locations and other response points to try and inform ourselves to the suitability of which one is more or less right than the other. So that's again a nice flat model. Now I've got a second model that we looked at, similar catchment, and this particular catchment is a little bit steeper. And if I turn on the surface information in this particular model, same process in building the model, but we can see we have a high point to the south and east, and a bit of a valley or low point directing the flows. Unfortunately, in this instance, straight through private property. This particular site was developed in the late 60s, early 70s, 1970s, possibly before some people, including myself, were born. But that being said, overland flow through this area is actually very important. So the local authority is definitely interested in understanding what a risk to both their assets and the private property are at play. And in this particular model, if I go back to my simple water depth playback and I hit play through this particular model, and I'm running a filter on this as well already, we can see that I'll clean off those contours. Water is at present, with the filter in play, confined to the streets itself, but shortly we'll start to see, and I'll just zoom in just a little bit. We're starting to see some flow that's going to bridge between these two roads, and effectively that's giving us that, what I'll call cross catchment flow. You'd like to think that the curb and channel would confine these flows, but look, we're getting depths of water that unfortunately are affecting a handful of properties and that unfortunately identifiable low point through the site. And the direct rainfall method is certainly a very appropriate tool to highlight that kind of relationship inside a catchment. So look, the interface, again, very quick to develop a direct rainfall model. Sure, there's a computer consequence, but I do also like to say that my computer works for free overnight. I like to go home to sleep. So does Bill. And having these additional computational procedures in play, giving ourselves a little bit more information to review is a good thing. And I really hope that the users of the software, or people who are interested in learning or getting into direct rainfall modelling, get something out of today's session. But that effectively finishes my side of the demonstration. But again, efficient, quick, and easy to deal with. They're the key take-home messages. I'll just jump back to the slideshow. So look, that brings us to the conclusion of today's formal part of the session. I'd really like to thank Bill for joining us. It's been an absolute pleasure having Bill come on board and share some of his knowledge and experience over this and the previous 2D webinars. It's been an absolute pleasure, and I look forward to going through any comments or queries that people do have. And thanks everyone for joining us.
And thank you.